Hello, I'm Srini Devadas. I'm a professor of computer science at MIT, and I'm serving as the guest editor for a special issue of IEEE Computer on cache coherence. I'm talking with Tushar Krishna, who's the first author of a manuscript that's going to appear in the special issue titled Single Cycle Multi-Hop Asynchronous Repeated Traversal, a Smart Future for Reconfigurable On-Chip Networks. Hello, Tushar.
Hi, Srini.
Thanks for agreeing to talk. I thought we would start by perhaps you giving the audience a sense of what on-chip networks are.
Sure. So to understand what are and why we need networks on a single chip, we need to understand the evolution of on-chip systems from the early 80s to today. So from the last few decades, the semiconductor industry has been driven by Moore's law. So Moore's law was a prediction by Gordon Moore, a co-founder of Intel, which says that the number of transistors on chip will double every 2 to 3 years. And over the years, computer architects have used these extra transistors to add more and more functionality on chip. And the smaller size of transistors has resulted in faster circuits. So our chips went from speeds of a few megahertz in the 80s to a couple of gigahertz by the early 2000s. So to keep the chip's power consumption in check, the increase in operating frequency in every technology generation was accompanied by a corresponding decrease in the operating voltage, since power is proportional to the frequency times the voltage squared. But a decade ago, we hit an inflection point. It was no longer possible to reduce the operating voltages of our chips, since we were already operating very close to the voltage at which transistors turn on and off. This was called the power wall. So the end of voltage scaling also led to the end of frequency scaling to keep chips within the power budget. So instead, computer architects decided to scale the performance of chips by using the extra transistors provided by Moore's law to add multiple simpler low-power cores on the same chip and run them in parallel instead of designing one complex power-hungry core. This is known as a multi-core chip. And since early 2000s, the number of processing cores has continued to increase. Commercial chips from Intel, AMD, and IBM today have 8 to 16 cores, while those from Tylera have 100 cores. Academic and industry research prototypes have also been demonstrated with 80 to 110 cores. Now in a multi-core chip, the various cores often need to communicate with one another since they are collaborating to run an application in parallel. And this is where on-chip networks come in. So an on-chip network is basically the communication fabric interconnecting the cores. Examples of on-chip networks include buses, rings, and meshes. For chips with up to 8 cores, a simple bus can be used to connect all the cores. Each core needs to arbitrate and gain access to the bus and then transmit its data to all other cores. The problem with buses, however, is limited bandwidth. Multiple cores cannot communicate with one another at the same time. So beyond 8 cores, on-chip networks have evolved to rings. Rings allow multiple source-destination pairs to communicate in parallel, but the problem with rings is delay or latency. So as the number of cores increase, the maximum latency through the ring increases linearly. So for core counts beyond 32, two-dimensional topologies such as meshes are preferred. So a mesh is basically a grid of wires with routers at cross points to facilitate the sharing of links. The distance between adjacent tiles is called a hop. So meshes offer a square root dependence of the maximum latency on the number of cores, and hence are better than rings. And moreover, meshes also offer path diversity, increasing bandwidth. So in this work, we use a mesh on-chip network as our underlying communication fabric.
Thank you, Tushar. Could you describe your current work on SMART, which I understand is an acronym?
Sure. So the goal of this work is to basically minimize on-chip network latency. So a high on-chip latency not only delays initial requests and responses, but because of dependencies, also bottlenecks additional requests and responses, leading to overall system slowdown. So let's see how two cores communicate via a 4x4 on-chip mesh network. So suppose core 8 wants to send a message to core 7, which is 4 hops away. So this message will need to go via 3 intermediate routers, 9, 10, and 11. And routers are bad because they add delay. Router delay is at least one cycle, if not more, in the best designs today. And this is true even if there is no other flow contending for the shared links. So the network latency is always proportional to the number of hops you have to traverse. And this problem can only become worse. Right? We are already talking about adding thousands of cores on one chip for the exascale era, and as we add more and more cores, the average number of hops between cores will go up, increasing latency. And we don't want to reach a situation where the on-chip latency starts becoming the bottleneck to scalability. So what do we ideally want? Well, ideally, if core 8 wants to send a message to core 7, there should be a dedicated wire between the two. We can design this wire to take a single cycle. So the network latency will always be just one cycle, and there will be no added latency due to intermediate routers. So if we want to run only one application on our chip, we can design a topology that's tailored to its communication pattern. But since we would want to run multiple applications on our chips, we need a shared network with routers. So we seem to have two extreme requirements here. At one end, we want a dedicated single cycle wire between each source and destination, while on the other end, we want a shared network to support multiple different communication patterns. So the goal of this work is to bridge these two extremes and realize a single cycle network traversal over a shared on-chip network. So in this work, which we call SMART, which is an acronym for Single Cycle Multi-Hop Asynchronous Repeated Traversal, the broad idea is to create a virtual single cycle connection between communicating cores. So even though the traversal is multi-hop via intermediate routers, we achieve a single cycle traversal. The basic trick here is that even though we have intermediate routers, they do not add any latency penalty because we do not latch the signal. Instead, we use a clockless repeater to drive the next link segment. The network latency now becomes independent of the number of hops. Moreover, because the connections are virtual, we can reconfigure the network and match these single cycle paths to traffic. That means we can create a virtually tailored topology for application A, then create another virtually tailored topology for application B, and then for C, and so on. So all the blue links here are single cycle paths. For all this to work, we need two key enablers. First, we need the underlying wire to support multi-hop traversals within a single cycle. And second, we need a network reconfiguration methodology. And I will describe both these next. So a standard technique to reduce the latency of long wires is to add clockless repeaters. That is, a pair of inverters at equal intervals. This is known as a repeated wire. So we performed an experiment where we did a layout of a repeated wire with a repeater spacing of 1 millimeters, which is our target tile size, at 45 nanometers. Next, we modeled a 128-bit network data path by placing 128 such repeated wires next to each other in parallel and gave a wire spacing of 3 times the minimum allowed by the technology. This minimizes the coupling capacitance between the wires. We then performed circuit simulations on these wires and observed that repeated wires can transmit signals up to 16 millimeters at 1 gigahertz. Now, if we replace the conventional clocked repeaters at every router by these clockless repeaters, this allows us to send signals up to 16 hops on the mesh within 1 gigahertz. And we call this hops per cycle max, or HPC max. The second part of our technique is the ability for the network to reconfigure to create single cycle multi-hop paths. So every router in our design operates in two modes, buffer or bypass. So in the buffer mode, it latches and buffers any incoming signal, just like the baseline router. In the bypass mode, it forwards the incoming signal directly to the crossbar switch, where it goes via the clockless repeater to the next router. So every router has two key control signals. The first is the buffer enable signal to determine whether to latch the incoming message or not. And the second is the bypass multiplexer's select line to choose between the bypassing message on the incoming link and the local buffered messages. So basically in the bypass mode, the buffer enable signal is off and the mux is set to bypass, while in the buffer mode, the buffer enable signal is on and the mux is set to local. So a multi-hop smart path basically consists of the source and destination routers operating in buffer mode and the intermediate routers operating in bypass mode, thus realizing a single cycle traversal across multiple hops. The router's reconfiguration control signals need to be preset before the message actually arrives. And this presetting can be done at different time granularities. For on-chip networks in the system-on-chip domain, such as chips in an iPhone, the application traffic is deterministic, and the entire network can be reconfigured prior to running each application in an offline manner. So if there is no contention along a path, the routers operate in bypass mode throughout the application duration. In case two or more flows contend for a particular link, the routers connecting these links operate in buffer mode throughout the application duration to enable arbitration for the link. For on-chip networks in the general purpose domain though, such as our laptops or servers, cache coherence traffic through the network is non-deterministic. And so the network is reconfigured cycle by cycle to adapt to the instantaneous traffic. So in this design, we use some extra bits on the control plane to help reconfigure the network. These bits are called SSRs for smart hop setup requests. So SSRs are dedicated repeated wires that connect every router to all routers in its HPC max neighborhood. So for instance, suppose HPC max is 3, then in the east direction, router R0 has an SSR wire up to R3, R1 has an SSR wire up to R4, R2 has one up to R5, and so on. And a router transmits the number of hops that its message wishes to traverse on its SSR wire. So I'll explain all this with an example. So suppose we have a router R0 that wishes to send a message to router R3 that is 3 hops away. So in cycle 1, it sends an SSR equal to 3. All routers now reconfigure based on the value of the SSR. The destination router R3 reconfigures into the buffer mode, while the intermediate routers R1 and R2 reconfigure into the bypass mode. So in the next cycle, R0 can send a message all the way to R3 within a cycle. Now let's take a slightly more complicated example. Suppose R0 wants to send a message to R3 as before, and R2 also wishes to send a message to R4. Both R0 and R2 send out SSRs to their neighbors. So now the challenge is that only one of these messages can be allowed on the shared link between R2 and R3 in a particular cycle. So we follow a fixed priority rule between the SSRs. All routers prioritize their own messages over messages from the neighbor 1 hop away, over messages from the neighbor 2 hops away, and so on. So following this priority rule, R2 reconfigures into the buffer mode to stop the incoming message from R0 and sends its own message out instead. So R0's message will prematurely stop at R2, while R2's own message will go up to its destination R4. In the next cycle, the stopped message at R2 can continue its traversal. So in conclusion, SMART creates opportunistic single-cycle multi-hop paths in the network. In case of no contention, messages can traverse the network within a cycle. In case of contention, messages might need to stop at some or all routers, but this will be just like the baseline design.
Great. Thanks, Tushar, for that nice description. Perhaps you can give the audience a sense of how you see this being applied to future multi-core architectures, and perhaps maybe some current limitations that you'd like to improve on.
Sure. So I'll start with by discussing the scalability of these designs and the expected issues that we see. So in this work, we looked at 45 nanometers. As we go to even smaller technology nodes, wires will become thinner, increasing their resistance and lowering their capacitance to the ground. Parallel wires can also be placed closer in smaller technologies, but this will increase the coupling capacitance. So the first thing we need to do is give at least 2 to 3x spacing between the wires, just as we did in this work, so that the effect of coupling capacitance is minimized. Once this is done, multiple studies have shown that the overall wire delay, which is the resistance times the capacitance to the ground, is expected to remain similar for these wires. This is actually contrary to the trend for transistors, which become faster at smaller technology nodes. However, this is not really a problem, because our chip dimensions are expected to remain the same due to limitations of yields, and our clock frequencies are expected to remain the same because of the power wall. So these three observations, that is global wire delay remaining similar, chip dimensions remaining similar, and clock frequencies remaining similar, indicate that it will continue to be feasible to go from one end of the chip to the other in 1 to 2 cycles at 1 gigahertz, even at future technology nodes. From an architectural perspective, smaller transistors will mean smaller tiles and more hops. So if we continue to design single cycle per hop designs, on-chip latency will become horrendous. But in a smart design, smaller tiles will translate to larger number of hops that you can traverse within a single cycle, which will end up in fact magnifying the benefits of smart. So in conclusion, I believe that a smart-like design will not just be feasible, but also be required in multi-core chips at future technology nodes. And finally, from a design perspective for multi-cores, I believe that the ability to go to nodes that are far away within a single cycle challenges our current notion of locality. We no longer need to optimize to keep data local or private within the tile for faster access, since multiple remote tiles can be accessed within a single cycle, increasing our locality neighborhood. This basically can pave the way for locality oblivious design, easing the burden on cache coherence protocols, compilers, and the operating systems from actively optimizing for locality, thus providing scalability.
Thanks, Tushar. The notion of locality oblivious design or locality oblivious algorithms certainly seems exciting. I don't really have any more questions for you. Thank you for submitting your excellent work to IEEE Computer Magazine.
Thank you, Srini.